All right, guys. So we roughly left off with the problem of calculating the velocity. Okay, I went over that rather fast, so I'm not showing my face for some reason. Here it is. Yes, I went through it a bit fast, but let's just see if you understand the idea. Actually, with one of you, we spoke about this feature. Have you ever been to a speed trap, right? How does a speed trap camera work in principle? Have you thought about it? Or maybe you can think of another thing. Have you ever seen a Venus flytrap? Yes, you like biology, you've seen a Venus flytrap. You know that that a Venus flytrap is this flower that closes upon the insect once the insect lands on the flower. But you know, the flower has this problem. It's very costly to close. And maybe if I'm not mistaken, once the flower is closed, it will never reopen. It will just digest the insect, and pretty much that's the end of that particular mechanism. How would it prevent itself from closing when, let's say, maybe an inanimate object falls upon it, like a leaf? Have you ever thought of it, guys? Some of your biology majors. How would it prevent itself from closing when more than when something not alive falls into its lap?
It's kind of like a motion detector. Something
Exactly.
that doesn't move, it will not close, so it's not alive.
That's right. If it doesn't move, it will not close. But what is a motion detector? So a speed trap can work in very much the same way. Think about it this way, right? So what is velocity, right? Velocity, the way you described it before, it's change of distance or change in position over change in time, distance over time, to say simply. Remember, that means what? That means when you say that implicitly, that you are assuming that the motion is uniform, it's constant, right? So if I say, people forget about fractions like this, right? If I said I moved 12 miles and you say you moved 6 miles, which one of us moved faster? It's not clear, right? Maybe I moved 12 miles in 2 days and you moved 6 miles in 1 hour. So you moved faster then, right? So to standardize, you need to report a given amount of distance traveled per given amount of time. Hopefully that's clear to you, right? So when I say something is moving at 2 meters per second, you're saying every second a distance of 2 meters is traversed. Yes? And something that is moving 4 meters a second is for that same second carrying more distance, you see? So you have to standardize to have the same amount of time. That's why you have fraction, right? So 6 miles per hour is the same as 12 miles per 2 hours, right? So basically double the denominator, double the numerator. Fractions capture the concept of constant speed very well. That's clear, yes? That's wonderful if it's clear. So how can you devise a sort of speed trap? You can do the following, right? If I mean that this is probably, it works probably much with a much more clever mechanism, but imagine that you have a sort of trigger here, and let's say you have a trigger here. Okay, so there is a fixed distance in between the triggers. You agree? So you take that fixed distance, and let's say at this point you turn on, you turn on first trigger, so that would be T1, and at this point you turn the second trigger. So distance divided by T2 minus T1, you understand? So you have, it's the timer, right? Timer, this is the amount of time that will elapse between your first trigger and second, and basically the same distance divided by large number of time means you are traveling slowly. If it's divided by a small amount of time, that means you're traveling fast. Do you agree? So that's a way that a Venus flytrap can do the same thing. I think it has hairs. I think I've seen that some sort of hair triggers that the fly has to touch a few of them within a certain amount of time. You understand? It touches one of them, and there is a timer in this, maybe chemical timer. It doesn't matter. Some sort of timer that within a few seconds or within a few moments, if the second trigger is touched or third trigger is touched, the flower will close. It's a way to try to predict that it's actually something moving, something that it wants to eat. Good? Same way a speed trap might work. I mean, you can devise different whatever it is, you can devise different ways of doing that, right? What will be activating the the activating and the deactivating of the camera. Okay. Now, that was just a review of velocity in general. Now, would anybody tell me what am I looking for when I try to calculate instantaneous velocity?
You're looking at a specific point in time?
Yes, we're looking at a specific point in time, but that's only part, right? Specific moment in time.
And constantly?
Say, sorry?
The constant of the velocity?
Well, but that's vague. What do you mean constant over the velocity? What am I looking for? Let's say when you're driving a car and you want to know how fast you're moving. You're looking at specifically what?
The velocity for that period of time.
The speedometer, guys, right? So yes, velocity is a bit complicated word. You have to, it has to be extremely natural to you. Understand, guys? So extremely natural, so you really know what you're looking at. You're looking at an indicator in the car that tells you how fast you're moving. If you could take a photograph of at any instant, you will see how fast a person is moving because the arrow is pointing, let's say, 60 miles an hour, for example, right? You could take a photograph inside of the car and you could see that 60. Yes, and that will tell you the speed with which the car is moving. Yes, guys? Now, you understand that what is a speedometer, it doesn't matter. It doesn't have to be the arrow. There is always something in nature that is supposed to reveal what the speed is. The speedometer could be built on any sort of principle, okay? And so when I want to calculate instantaneous velocity, I'm trying to figure out what the speedometer for that particle or the car or that moving object is showing at the moment when I press pause. So for example, in here, I am interested with what speed the car traveled past the traffic light, okay? So I realized based on this animation that if I pause the car at 2, the car is exactly by the traffic light at 5, right? And at the moment where I press pause in this video, I want to know what's the velocity of the car. What is the instantaneous velocity? What is the arrow of the speedometer showing? Yes? So far, so good, right? And notice that if I have a video of this car and it's, let's say, moving along a ruled number line, I have a function that translates time to position. You understand what that means? To say a function translates time into position is just a fancy way of saying that if you select a moment of time, the car is in a particular place. So I selected time 2, the car is at 5. Here I gave a list of values. At 0 seconds in the video, the car is 1 meter. I mean, let's say maybe it's a toy car, it doesn't matter what it is, right? Let's say it's measured in meters and time is measured in seconds. So I observed that at 0 seconds in the video, the car is in position 1. At 1 second in the video, the car is 2 meters from the beginning, from this point, right? At 2 seconds, it's 5 meters away. At 3 seconds, it's 10 meters away. And remember what we were able to do, because this formula is, because this relationship is simple enough, we suspect that the general position in terms of time is given as xt equal to t squared plus 1. Do you remember that, guys? Do you see how we do that? You see it works. 0 squared plus 1 will give me 1. 1 squared plus 1 will give me 2, etc. Do you see that all those values are matched if this is the function? Right? I have very few values. Naturally, maybe that's not the right function, but heuristically, imagine you play this video, you could experimentally verify that that might be the function with which this particular car is traveling. Yes, we have, this is called position function. Do you see that? It's where the car is located on the x-axis as a function of t. Good? Wonderful, guys, amazing. Now, what is it that we want to do when we don't have the speedometer? How do we get at it? We have two ideas here, right? So again, you should just, if you observe, you see every change takes some amount of time to happen. Do you agree? Every change. So things grow or get older. Any chemical reaction will take some amount of time. Sometimes the amount of time is very short. Sometimes it's very long, but this seems to be true. If you give any phenomena very little time, there will be very little change. Okay, and very little time is relative to the particular phenomena. Yes? So the next idea, guys, how do I find instantaneous velocity is this, right? I might I might take a moment of time. Look at it. You see, I draw it here. And I call it 2 hat. The reason I call it 2 hat because it's supposed to be my best approximation to 2. Do you understand? It's like basically you try to get this point as close as possible to 2. And then you have a time interval. Yes? This time interval, the change in position over change of time for the time interval would be given by x of 2 hat minus x of 2 divided by 2 hat minus 2. Are you in agreement with me, guys? This is what? This is the change in position. That's the distance that was covered, right? So the distance that was covered, maybe it would be this distance. I don't know, right? Maybe that's the distance. This is x of 2, and maybe this is x of 2 hat. So we take the amount of distance we traveled and divide by the amount of time traveled, right? Which is the difference between 2 hat and 2. You with me? Now, why is this a good why is it a good approximation of the actual instantaneous velocity? Would anybody tell me? Why is it a good approximation when 2 hat is really, really close to 2?
Well, because there is not enough time for any significant change to happen in that time period.
Amazing. Thank you, Alexandra. So you heard it, guys. Yes. So if you create that's why we select a very tiny interval, right? If the velocity were constant, you could have selected any interval, but because velocity is not assumed and cannot be assumed to be constant, you select the tiniest interval you can for time, because little time means little change in velocity. You didn't have time to accelerate or decelerate if this interval is sufficiently small. Okay. So let's say, so Grant, so the numerator is the change in position and the denominator is change in time. So you wrote numerator on the bottom. Yes. Yes. Change in position. That's, you see, guys, one thing that people get confused is they imagine that mathematics is difficult because of the symbols, but the symbols are just like letters. Do you understand? Just like you are learning to read. What do? I look at the symbols and I think, okay, it's a story. I see what's happening. And then I translate the story into a visual. Me personally, I'm very visual. You can also translate it into smells or sounds, but I am very visual. Yes. Some people, maybe Bullen will understand music far better than me. It seems you have a lot of music equipment. I'm very tone deaf, unfortunately, but you have all those things, those sensors. You translate it to the sensors, and then you create a simulation in your mind, and then you translate the result of the simulation back to symbols. Good. So 2 hat is not, you see, look at it. You understand that 2 hat is a sort of concept. It's not an actual number, because you see this particular choice of 2 hat might not be good. Maybe that was enough time for acceleration. You are trying to, we're going to talk about limits in a moment, right? You are trying to create the closest possible approximation to 2 you can, because the smaller this interval, the less likely there was any change. You understand? If you could select 2 hat equal to 2, it would be wonderful, but there is then division by 0. So what you do is you try to be a perfectionist. You squeeze the interval more and more and more, right? Until there is no change. That's what you do in practice. In practice, you slide it until you see that if you slide it closer, you don't see any difference in velocity. You understand? I slide it closer, no difference. Slide it closer, no difference that I can detect. Wonderful. Good. I hope it's understandable, guys. You see that this is the concept of instantaneous velocity is not difficult. I hope you understand that, right? Once you have the visuals, it should be not complicated. Little amount of time, the velocity is essentially constant because there was little time for it to change. Good. So what is that instantaneous velocity for? Yes, you see, the visual is helpful. So you see that here we selected the difference. This basically 0 was a bad 2 hat. 1 was pretty bad 2 hat because you see that we have different numbers here, right? And what is a good 2 hat? Well, the best way to think of it is you are just selecting it symbolically. Solve it symbolically. You see what I do? I say x of 2 hat. I'm pretending that this means I selected a number very close to 2 for which it's very good. It's symbolic. You see, this can change its meaning. It can be 2.00001. It's whatever you like it to be, right? I'm just going to try to detect the pattern. So look at it. X of 2 hat, by definition, will be then the number squared, the time squared, plus 1. and minus the 2 squared plus 1. One thing, guys, don't simplify. There is no reason to simplify anything here, okay? Many of you right away want to say 4 plus 1 is 5. That's a waste of your time. Don't do that, right? Because look at it. I will group like with like. Do you see what I do actually? I will give you in a moment another question while you do the calculation. But I group like, look at it, something squared with something squared, right? And I group this, which does not have a square, with like, right? So what happens when I group it together? What do I have here? I have here 2 hat squared. Let me have it in red, actually. I have here 2 hat squared minus 2 squared. You remember what 2 hat is? 2 hat is imposter 2. 2 hat squared minus 2 squared. And on the denominator, Bullen, please go ahead.
So I'm following you. The only thing I just need a little clarification on is just in the second part of the equation, where you get 2 hat square, what is that, -1 minus 2 squared plus 1.
Yes.
Just when we converted from the first half to that half, if you could just run, if you could just.
Sure. So guys, so this with this algebra thing, so you can stay after class. I can try to help you practice it. That's a sort of right. So what happens is this. You see, let me actually write it separately. Here, you see what happens. So you have 2 hat squared plus 1 minus 2 squared plus 1. Now you can distribute the minuses here. So you have 2 hat squared plus 1 minus 2 squared minus 1. Do you see that? So
yes.
The ones, they cross out. They disappear. The constants disappear. And I'm left with simply 2 hat squared minus 2 squared.
Minus 2 squared.
Yes. And this I will factor in a moment. You see, this I will factor in a moment. So that would be 2 hat squared minus 2 squared. That's 2 hat minus 2 times 2 hat plus 2. Yes? Good, guys?
Mm-hmm.
That you see how to factor it, right? So those things I mentioned, appendix A through E, you can try to review that. I can try to help you with those ideas. And I don't know, I mean, to me, if I understand why that works, I can teach you why, for example, what is multiplication in numbers. We spoke a little bit about constructible numbers, those that stayed in office hours. If you are interested, we can talk about what numbers, how they originate, geometrically speaking. Okay. So this is what we have, guys. Yes, you see that? We then have 2 hat squared minus 2. I factor it out, and now look at it. It's multiplication. So this number is not, it's a fake 0, so I can cross it out. And I have 2 hat plus 2. And now, what is 2 hat? 2 hat is very similar to 2. So I predict that what I'm going to get is the velocity 4 meters per second. You see, because this is kind of like 2, and this is 2. Together, this is becoming. You see, it's striving to be 2. Together, it's 4. It's striving to be 4. And the instantaneous velocity is 4. Okay, let me give you a quick exercise to see if you can do it. I will give you little time, so don't get worried if it's too short. It's just because the class is so limited. So suppose that we have this position function, guys. Okay, we have x of t equal to 3t squared minus 5. Okay, that's the particle is moving with this formula, right? That's how it's moving. So please tell me, 1 second. So please tell me what would be the velocity at 1 second in the video. And by the way, you can right away do 2. It would be better if you can. What is the general formula for the velocity at any given moment of time t? Because if you can answer 2 right away, you know in particular what happens when t is equal to 1. All right, guys, so I'll give you 5 minutes until 6:30. Try to solve it, then we'll solve it together.
Is that an X or a 5? No, S or a 5. I'm not
Where?
understanding. The last number.
The last,
-5?
well, it has to be a 5, of course, right?
Oh, okay. Yeah, thank you.
Yes, S would be meaningless. Let me, if you prefer, I'll write another one. So nicer 5. Yeah, that's better, I hope. So is V1 is 1 second, and I'm not sure what you mean, Sophia. Wait 3 minutes, and I will try to explain all of it. Well, Abhishek, by the way, you should sleep sometimes. Abhishek, yes, but we haven't defined derivatives yet. It's just such a beginning of this class. So we don't know derivatives, we don't know the symbolism. We need a sort of intuitive way to describe what's happening. Okay, good, Irinushka. All right, guys, I haven't given you a lot of time to think about it, but we can do that in office hours. You can have all the time you need. And if you have the strength of will to stay, then, you know, we will practice it at your pace. So V1, okay? Let's solve the first one. Again, remember the formula is x of t equal to 3t squared minus 5. Okay, so we want to know what is v of 1. Would anybody guide me how to set it up? What do I write? If I want v of 1, that means I want instantaneous velocity at 1, the speedometer at 1. And how would I get to it? We have the position function here. How do I get to it?
We need a second one and a hat, one with a hat.
Exactly, right? Precisely. You see, we just take the difference of x1 hat minus x1. divided by 1 hat minus 1. You see, guys, the formulas are obvious when you know what they mean, right? We are taking, what is the numerator? Numerator represents difference in distance. So in other words, difference in position. That's distance traveled, right? And the denominator represents amount of time it took to travel. Now we want the amount of time that we compare to be very small. 1 hat minus 1 is a very small number. 1 hat is very close to 1, yes? And so what do we do now, guys? Look at it. So now we have, what is x1 hat? This is 3 1 hat squared minus 5, yes? And x of 1 is 3 times 1 squared minus 5, right? What is the t? It means just plug in any time, and that will tell you the position for that moment of time.
Mm-hmm.
Divided by 1 hat minus 1, yeah?
Mm-hmm.
And what do we get now? That should be subtraction. Sorry, there says minus between. So
Fives cancel out again.
Yes, fives will cancel out, guys. Constants will always cancel out. I hope you see that. It's basically minus 5 minus minus 5 at 0. And then we just, we group like with like. So we are seeing here 3 1 hat squared minus 1 squared divided by 1 hat minus 1. Yes? And when I can factor out, this is a difference of squares. It's nothing hard, I hope, guys, right? So it's 3 1 hat minus 1 multiplied by 1 hat plus 1 divided by 1 hat minus 1. Now I can cross out 1 hat minus 1. Notice, because it's not truly 0. Do you agree? 1 hat minus 1 is not 0. It's just something close to 0, but it's still fine. We can divide it. You see, guys, that's why I wanted you to understand what is division by 0, right? So at some point as a student, maybe like you, I could not, I mean, in high school, right? I took calculus. I was able to carry procedures, but I was not interested. So I didn't understand. I just heard some sort of rumbling echo, like you cannot divide by 0, but then you can divide by 0. But I hope you are able to understand that we are never dividing by 0 here. Yes, that's what we do here. We just have a number close to 0. We're using the philosophy that if the time duration is short, then there is no change essentially, and velocity stays the same. So what do we get now? 3 times 1 hat plus 1 is what we are left with. 3 times 1 hat plus 1. And here I'm just using approximation. When I say equal to, look at it, it's like roughly like 3 times 2. Do you agree? 1 hat is a number similar to 1. So we're predicting that the limit will be 3 times 2, or 6. If it's measuring in meters per second, it's 6 meters per second. Good. Now look at it. I wasted a lot of energy doing it for the particular number 1. I don't want to repeat this process if I were asked to find the velocity at 2 or at 3 or at minus 5. I don't know, at any number, right? Or at pi. I don't want to repeat the calculations at different moments of time. So what do? I do this. Look at it. I want to calculate a general v of t. Right? You understand? By doing that, it's like I'm solving for, look at it, you don't be confused by this letter t. All it means is I have fixed a moment of time. I want to know how to figure out the velocity for that moment of time. And I label it as t because it's arbitrary. Right? It means just any moment of time. Do you understand what is a variable, guys? Right? So when I say, well, when you say Homo sapiens, right? Homo sapiens, an intelligent species, intelligent men, right? Well, men is a variable. Men means intelligent you. It goes over every single person. That's what t does. T goes over every single number. Understood? So how do I calculate v of t? Would you help me set up the formula for v of t, please?
Would it be the same as the previous one?
Obviously, it's the same.
Yes.
I
You
mean,
just
the
added to
question
t
is,
instead of 1.
so what do I write here, please? Just obviously it's the same. We're doing redundancies, but I use it.
X per, yeah.
So it would be x
T parenthesis
t hat
Hat.
minus x
Minus
of
t.
t.
Oh, yeah.
Thank you. Divided by t hat minus t. You see, just instead of 1, I just focus on some arbitrary number t. And when I carry it out, what do I get? I get 3t hat squared minus 5 minus 3t squared minus 5 over t hat minus t, yes? And when I simplify it, what do I get? I get here 3 t hat squared minus t squared divided by t hat minus t, which is what? 3 t hat minus t hat plus t over t hat minus t. Yeah? I
Yes.
factored squares, guys. You see, so one thing, guys, that you might be very good students, but one thing that always gets people is what was their past, right? The past always comes to haunt you. And that means that if you were not practicing algebra, we're not thinking about the material, you have a lot of thinking to be doing now. Because it's very easy for people to make mistakes when it's not automatic, right? So we cross this out. And what do we get? We get 3 times t hat plus t, which, you understand now I can say this is the same thing as 6t. Do you agree? You understand how I now converted the t hat to t again, right? So what is it? It's basically, I'm saying it's now the same as 3 or t plus t. So that's the same as 3 times 2t, in case you're confused. And that gives me 6t. You understand how I do that, yes? So there's no magic. You see, why do I convert t hat to t now? It's just because I know what I'm talking about. It's just a communication. I'm just saying that now I see that the answer is 3 times the fake t plus the real t. But the fake t plus the real t is essentially twice t. They are very similar to each other. You understand? I'm talking about similarities. T hat is striving. We're going to do it with limits. It's striving to be like t. It's an imitation of t. Okay? So we have that the answer is 6t. Do you understand what that 6t means? It means, for example, what is v1? All I have to do is take 6 and multiply by 1. What is v7? All I have to do is take 6 and multiply by 7. Multiply the time by 6 and you get the speedometer value. You understand?
Mm-hmm.
That's all this is saying. So when I say 6t, it's just saying find the time and multiply it by 6. It just gives you the procedure to find the speed at any given moment.
Professor, do you mind giving us another example?
Obviously, I'm going to give you one more example, but this one's slightly harder, yes? And in office hours, easy, hard, I mean, all of them right now are similar. And again, we will talk about limits in a moment, and we will talk about this topic again and again. We will talk about velocity throughout the class, okay? So here is another example, guys, slightly harder. X of t equal to minus 5t squared plus 14t plus 17, okay? This, I want you to calculate. I don't want to do the particular times. I mean, come on, you can do it this, right? You can calculate right away v of t.
Thế là 唔識做，完全唔識。
Okay, beautiful. Wonderful, Moshe. By the way, guys, well, one more minute, okay? All right, time. So in office, we can take longer time, guys, but here, so Jasprit almost right? You have part of it correct, but it's not completely so. Here is how we do it, okay, guys? First setup. You agree that the setup should be, we evaluate the position at some time t hat minus the position at the time t divided by t hat minus t. Okay, don't memorize some sort of formula like this. You see, I mean, somebody else could write it with different notation. The idea is what? I take difference in position divided by difference in time, where the two times are very close together. There is one time t, and where I'm interested to find the velocity, and another time t hat very close to t, an imposter of t. Somebody says we can see the screen. You mean you cannot see the screen? Can you see the screen, guys?
Yeah, we can.
Okay, good. Agreed, guys? So let's write it out. What is xt hat? That's minus 5 t hat squared plus 14 t hat plus 17. Put it in parentheses. Minus, in parentheses, minus 5 t squared plus 14t plus 17. Plus 17. divided by t hat minus t. Yes? Now, I will not, I will group like with like. You see, look, what is like with like? You see that this object looks very similar to this object. This looks so similar to this. And this looks so similar to this. You understand what I do? I just bring things that are similar together, segregating them from the different. So what we have here is, and then I can look at it. Look at the box. It would be minus 5 factored out, so it would be minus 5 multiplied by t hat squared minus t squared. So it's minus 5 t hat squared minus t squared. Yes? Do you see that, guys? I hope you see, this is basically foiling. You see that those are the steps that some of you are already having problems with, but that's pre-calculus, you understand? So for that we need to really hammer in if you're having those problems. You have to do a lot of those exercises. You see, look at it. I just have this box and minus this box. I can factor out a minus 5 and I have this. Now, plus 14 t hat minus t, and then plus 17 minus 17, which of course is 0, divided by t hat minus t. Okay? Now what happens now? Look at it, this is 0. And here I can carry out a simplification, right? So let me simplify it a little, maybe here. Look at it. I can cross, this is simply 0. I can cross this out and this out. If I cross t hat squared minus t squared, I'm left with t hat plus t here. And here there is nothing left. Yes? Make sure that you respect your arithmetics so that you don't make silly mistakes. And what am I left with? I am left with...
Why do we cross out the first where the t hat squared minus t squared?
Well, because I factor it out. I mean, it's really t hat plus t. So if I factor it out, it will be t hat minus t.
And t hat plus t.
Yes, and t hat plus t. So when I mean I can simplify it, and I am left with t hat plus t. You see it? No?
Yeah, but then you canceling out one t hat minus t and then another t hat minus t.
Well, okay, I'll do it slower.
Because it's the same. If it's t hat 2 minus t hat 2 is 0, so he's crossing it out.
Oh, okay. Oh, okay. Sorry.
Let me be careful. I'll do it slower in case you have problems with it. But that's what I mean, guys. You see, if the algebra is kind of quick, it's like, it's very difficult to read letters when you're learning a new language, right? So you read each letter separately and it's painful, but when you are comfortable with the symbols, you just move faster. So what I mean
so it would be like 9?
So it would be, well, here it's minus 5, right? Look at it. I can write it as minus 5. Here I have t hat minus t, t hat plus t, right? I'm not skipping that step since you are having problems with it. Plus 14 t hat minus t. I will not copy the 17 minus 17, it's 0, right? So we have this divided by t hat minus t. Do you agree that I can factor out in the numerator? Look at it. I'm going to underline it so that you can see it again. I can factor out this and that. Okay? So I will write what I factor out in red. So look what happens. This is minus 5 t hat plus t plus 14. And all of it, look at it. Here is the parenthesis. All of it multiplied by t hat minus t. You see, I factor it out. And here again, what I factored out is this segment. Only through multiplication can you cancel, can you divide. So now this is t hat minus t. Yes? Now it's numerator, this rectangular parenthesis multiplied by t hat minus t divided by t hat minus t. So I can obviously cross it out. So I can cross this out and this out. You see, it's the same thing I did before, I just did it fast. But here, this is what we get, yes? And now I have this answer. I have now minus 5 t hat plus t plus 14. And to finish it off, guys, what do I mean by t hat plus t? Obviously, this is supposed to be like 2t, right? T hat plus t is like 2t. So if you prefer, I mean, it's not exactly equal. It's kind of like this. It's what it strives to be. So it's minus 5 to t plus 14. And what you're getting is minus 10t plus 14. Good? Minus 10t plus 14 is the answer. What does the answer mean? It means that if you're given a moment of time, so for example, if you want to calculate what's the velocity at 1 second in the video, you just take minus 10, multiply by 1, and add 14. You understand? This tells you what to do to calculate very quickly any velocity at any given moment of time. All right, so we can do more questions of the sort and slower if you want after class. But now let's continue with the material. Okay. All right, so the hat notation is not a notation we will be using, okay? It's just my notation to, again, to introduce you to this idea, to the velocity problem before I talked about limits, okay? So t hat is not, you see, t hat is not really a number. T hat is an idea of something striving to t, right? Becoming t. So in calculus, for reasons of the same sort, we need to distinguish between two types of operations. So you have the operation of evaluating a function at a constant at c and taking the limit as x goes to c, okay? And the first means something very obvious. You just plug in the number into the function and you get another number. This now is not plugging one number, c, but plugging numbers that are ever closer to c. So it's plugging multiple numbers that are ever better imitations of c. They are fake copies of c. Okay, let's try to see that by an example. What are you doing when you calculate limit and what are you doing when you calculate the function? Okay, so look at it. If we take a very simple function, f of x equal to 2x, then if I plug minus 1 into it, it's just 2 times minus 1. Do you agree? It's minus 2. What is it that I'm doing when I take limit as x goes to minus 1? This is roughly what happens, you see? I do not plug a minus 1, I plug a fake minus 1, you see? So minus 1.1 is one instance of a fake minus 1. So it's 2 times minus 1.1 and you get minus 2.2. But obviously you can do better. So you plug in minus 1.01, that's a better imitation of minus 1. And then what you get is minus 2.02. You can do better and you get minus 2.002. Do you see? I am improving my approximation. What I'm doing here is I'm never plugging in minus 1, but rather an improved approximation. Again and again, I plug improved approximations of minus 1. And I just notice the tendency. Do you see what the tendency is? That as x is striving to become minus 1, f of x seems to be striving to become minus 2. Now, in this particular case, look at it. The results are the same. If I plug minus 1, I get minus 2. And if I carry out the limit process, I also get minus 2. But don't make the mistake of assuming that limit and plugging in is the same thing. Novice students always say, oh, just plug in the value. It just happens that in this case, the two different processes end up giving you the same end result. You understand? You plugged in minus 1, you got minus 2, and you plugged in approximates of minus 1, and you got minus 2 as well. But the process was entirely different. Okay? Limit is all about the process. Very often, once you get complicated functions, they will be nothing alike. Limit and the value are nothing alike if you carry out operations in the wild. Those are just very simple functions, very introductory, very basic, okay? There are special class of functions for which doing the limit process gives you the same result as just plugging in the numbers. okay? So let's look at another example. You see this, guys? This function is f of x equal to x squared plus 1 if x is not equal to -1, and it's equal to 3 at -1. So clearly, what is, by the way, what for this function is f of -1? So for this function, f of -1 is what? Help me.
1 minus x squared.
Well, careful. We use this formula if x is not equal to
Oh,
1.
I'm sorry.
So the answer is 3.
3.
You see, the answer is 3. What do you think will happen if I carry out, without me even saying, let's see if you can see it before I say it, what will happen if I push x towards -1, x approaches -1 of f of x? What do you think will be the number that I will get? Okay, somebody says 3, but be careful. So, okay, Erin says 2, so, okay, another person says 2, Sarah says 2, okay. So what you will get is indeed 2. Look at it, why do I get 2? It's because, which formula am I using? I'm using this formula, right? What is my thinking process? I plug, when I think here, when I take limit at -1, I think -1 hat squared plus 1. You see why? Because if x is approaching -1, it's not equal to -1. Therefore, I'm not using the bottom formula. I'm using the top formula. You see, I'm using this formula for all values that are not equal to -1. Okay. So symbolically, I am producing an imitation of -1 and plugging it in here. And I suspect that squaring an imitation of -1 and adding 1 to it will give me a number that's very, very similar to 2. So my prediction is that the limit will be 2. Do you agree? You see what I do? The 2 hat, I mean, it's all just really same symbols. It's just idea. I'm plugging in not the actual number -1, but imitations. And the imitations are ever better. Okay, let's look at it more carefully. Look at it, guys. Here is what happens. You see what's happening? Look at it. I'm plugging imitation of -1. Do you see this -1 hat? It could be any one of those numbers, okay? So as I do this, it's like, well, that's what I mean by -1 hat. It's a sort of fluid idea. It's this, and it's this, and it's this. It's as good imitation of -1 I can get. The best counterfeit, okay? And look what's happening when I plug those counterfeits. Do you see what's happening? They're not 2. You agree? This is not 2. But they look more and more like 2. Yes? So the limit gives me 2. Now observe, look at it. In this case, evaluating the limit gave us a different result than plugging in -1. You agree? They are different processes. They do not always give us the same result. So let me try to explain to you what I actually imagine. Tables, that will be important for delta epsilon in case you decide to study it. Last semester, I spent a lot of time talking about it, but you know, there are a lot of topics. So this time, if you're interested, delta epsilon will be a recording or optional topic in office hours. And of course, it will be an extra credit on the final. No, I mean extra credit on my exams. I'm not sure what will be the final, right? It will be extra credit on my exams. Let me actually explain to you how I visualize limits versus evaluation of functions, okay? So it is this drawing. I'm actually going to give you another one, okay? Just to illustrate what's happening, okay? I think of the x-axis as water. Imagine that the x-axis is water and the y-axis is just this wall, okay? Let's suppose that my function is f of x equal to x squared plus 1, okay? And I want to calculate, let's say, I want to compare this. I want to compare f of -1 and limit as x goes to -1 of f of x. I want to draw them, okay? So obviously the point of interest is -1, okay? The point of interest is -1. Let's mark that point of interest. So this is -1. Yes. Now here we have the water gun. Okay, this is my water gun. This is my f of x. Now when I evaluate f of -1, what am I thinking about? I am thinking that I am feeding this gun, this water toilet, I'm feeding it the input -1, and the input -1 is launched onto the y-axis, and you have one hit, right? So this one hit point, it's f of -1, which is in this case 2. You agree? It just hits the point 2. You understand? So when I evaluate, I plug in one particle, one water molecule into the gun, and that's what gets launched. I'll just write -2 here. -2 is the place where the particle lands. Yes. What
Not
am I?
-2, +2.
Yes, +2. Thank you. 2 is the place where the particle lands. Yes. What am I truly doing with limits? Tables, in the table, I selected only a few values and then I created a sort of sequence. That's not really how I think of it. I think of plugging in all the particles that are close to 1 simultaneously. So imagine that that is the interval that I plug. So they are all fed in. And, like you have all of them coming in. And you have those particles squirting in many directions. You understand? So you have a huge puddle, and you are prevented from squirting -1. There is a plug. You're not allowed to put -1 when you take the limit. You're allowed to put only the values nearby. But you see this pipe, guys, it's not a good enough image. You see this pipe is supposed to get narrower. Look at it, because this is some approximants of -1, but you could do better. Why not take those approximants of -1, right? So why not take a narrower pipe? And if you take a narrower pipe, then the currents will get narrower. You understand? It's a continuous stream. You have countless particles smashing against the wall. You have a stain, yes? So to say that a limit exists is to say that the puddle is going to get narrower and narrower. If you're saying that the limit as x goes to -1 of f of x equals to, if you're saying that this will equal to 2, you are claiming that the puddle, you see this stain on the wall, the spray of the gun will focus around 2 until it looks like it's going to 2. So when you do limits, you imagine, you can think about brushing your teeth. When you brush your teeth and you open the faucet, if the current is very large, it's spraying around. Not everything is hitting the sink, right? Not everything is going into the sinkhole, right? And now then imagine you're closing the valves of your faucet, and the stream gets thinner and thinner and thinner, and it gets into the hole, right? Into the sinkhole. And that sinkhole is that limit. You see, with the center of the sinkhole is the limit point. You understand? You have this visual, guys, that you're launching, in limits, you're launching countless particles into the function simultaneously. Okay, so that analogy is what I use to explain delta epsilon. So it's a sort of engineering way of just basically what you imagine is that you have like a laser or a water or some sort of beam, and your goal is to get it focused to within some tolerance.
So you can't really get it on the bullseye, but I guess the idea is to get it as close as you can.
Well, the idea is you can get it arbitrarily focused. Do you understand? So let's say you need to, let's say, what is your, so it means that you specify, let's say you specify this to be your bullseye. So in other words, if you would say for somebody, this would be a good approximation of 2. You see, all numbers in this green region look like 2. I mean, I drew it purposely big, but imagine this circle was 1 micron, 1 micron radius. You understand? 1 micron, you would not see it. It would look to you like a dot. You see? So just make the circle narrow enough. That's your epsilon. And then you have to have a procedure to how to squeeze the input so that the current hits into the green region. And no matter how small is that green sinkhole, you can always squeeze the input pipe. You see, this is the input pipe. The input pipe is this thing, right? You can always squeeze it enough around -1 so that all the droplets are hitting the sinkhole. They're going into the sinkhole. You understand? And if you understand that analogy, you could, once we talk about it, understand the exact definition of limit, what they are, which took a long time for people to develop. There were a lot of fighting about calculus. You see, it was not something that right away was expected or understood or adopted by everyone. Good?
Yeah, thank you.
Good. So you have a visual of what a limit is. You see, I don't think of it as a sequence like I do in the table. I think of it as simultaneously launching lots of particles, in this case, particles approximating -1.
Yeah, it definitely became much clearer after the sync example for me.
Yes, good. Good. You see, guys, I hope you have that visual, because that's all it is. You see, if you have those visuals, then you understand this idea, and you can understand it sometimes better than people that only understand it formally. They can just kind of describe it or prove, but they don't really know what it is about. The bigger picture, but of what bigger picture? Of life, of your existence, of why we are not meeting. Bigger picture of what? Yes.
Do you hear me?
Yes, I do hear you, Nicole.
Yeah, I get the concept, but I'm losing like where this all comes in. Like, you remember you did the car example?
Yes, yes.
And again, like the bigger picture, if you get what I mean.
Oh, you mean what is calculus? Yes, that's an amazing question in essence, right, guys? You're here. I mean, it's not true that all of you have to take it. I mean, the school makes you take it. It's not true that all of you will use it for life or need to use it for life. I hope you will. All right. It is definitely it became part of me, or other mathematics does. It gives you insights that other people do not have. It might, that's at least my hope, get you more even spirited and impervious to some propaganda, even though that's not completely true, because usually things are very complicated. Okay. But the bigger picture is, you see, you're looking at the screen, you're seeing videos, you're watching movies, you're listening to music. All of it is built on ideas that are the same. You can argue whether or not calculus built them or those ideas built calculus, but all of those ideas are related to calculus. They're the same ideas. You understand? So the idea is very simple. Can you build up the universe out of something very simple and very trivial? That's pretty much what calculus is about. Okay, so we will analyze curves. What is a curve? We can think of curves as mini microscopic line segments. Okay, so, or if you watch an image, right? What are all the complexities of colors? Those are small pixels that are just a few shades. You see, I forgot which ones. Red, some other shape. You might know it better. I don't remember, but you know, like some sort of colors. Sound can be built out of very simple waves. Very complicated sound, any sound, not only any sound, any light can be built of very simple ways. So the idea of calculus is playing with Lego blocks. Okay, what is the simple Lego block that you will need to build up the particular phenomena that you try to study? That's the big idea of what is calculus and what it's built on. You see, so it's somewhat intuitive for me. It's also, you see it on the screen. So you see that, let's say you play video games, right? And you've seen modelings of shirts. So in a video game, somebody is running and the shirt is moving, yes? Or the person is moving. What is that person? It's built of tiny triangles, a mesh of triangles. And triangles are simple shapes that you can manipulate and move around with basic algebra. Do you understand? You just have many of them to move. If you have billions of them to move, you can create complexity. So the idea of calculus is the idea that you can generate very complicated simulations from very, very simple pixels or very simple blocks. Okay, and the search in calculus, the different studies in analysis, is what are the simple blocks? What are the simple blocks for the particular study? What should I build my model from? That's the bigger picture. This is just some tools that we will use along the way to describe that bigger picture. So limits are very descriptive. They describe approximation. You see, they describe, why do we need limits? It's because they describe improving a particular block to make it more and more and more like the thing that you're trying to simulate, okay? It just gives you the language of doing that, okay? So for example, imagine you have very bad resolution made of many squares, and then the squares get smaller, and then suddenly you see it's an image of a person, okay? You've seen such images, right? So when you have the faces blurred, there are kind of big squares like that, okay? So that's the big picture. And that's an amazing question. Thank you for asking, but we will return and mention that many times, okay? The big, yes. So Grant, you're saying, so once again, we can't just plug in the number and get out the number we are looking for, because not every function will be so simple to just, well, it's always the question is what it is. You see, I never told you that you have to use limit. All it is about right now is just to explain what's the idea of limit. What is this operation supposed to do, okay? So when I say limit as x goes to -1, there is no reason for you to apply this operation. But if you apply this operation, you're talking about this picture. You see, you're talking about plugging in numbers close to -1 into the function. You see that, guys? Right? So whether or not you decide to use that tool for the particular question, for the particular problem, that's up to you. But the tool is, this is the explanation of what the tool is doing. Okay. Okay, so this is that picture. Let's move on. Okay. Yes, it depends. Well, you can either, so what I just explained is this: if your task is to plug in a number, maybe you can do it, maybe you cannot. It's a separate operation from evaluating the limit at that number, okay? And I just try to explain what the operation of evaluating limit is supposed to do. Okay, it doesn't mean that it's useful for that particular example, or you gain an insight if you apply limit for a particular example. It's just a sort of concept, right? It's like in English, you see, you have to learn. You remember, have you ever learned what is present progressive? Like, let's say, I am speaking, right? As opposed to I spoke, right? So it's just part of the language. So what you're doing is you're learning the little bits and tools of what they do, and then you can decide what you do with them. Okay, so here is one-sided limits, okay? We need to talk about one-sided limits first, okay? So if I am going to approximate C, I can also approximate C in one dimension. It's one-dimensional space. I can have only one parameter to move in. I can decide to approximate C from below. In other words, that would be written as x going to C minus. And I can decide to approximate C from above. That will be C plus, you understand? So if x goes to C plus, it means that my approximants are always slightly bigger than C. And if it's C minus, my approximants are always slightly less than C. Good? Let's try to figure out this evaluation, right? Let's try to calculate, guys, this is the example. You see it? Calculate f of 3 and the two limits, please. Okay, Grant to say 5, 6, okay. Okay, thank you, Grant. You're pretty fast with your smiley face. All right, guys, right? This is not a hard question, yes? What is f of 3? Let's begin here. You see, this is the function. It's 2x for all values of x less than 3. Do you see what it means? It means that if I want to evaluate at a number smaller than 3, I use this formula. If I want to evaluate at 3, I use this formula. So what is f of 3? Well, that's obviously 5. Agreed? No problem there, right? Because if I plug in 3, it's 5. Now, what would be the next b? X goes to 3 with a minus on top. It means, which of the formulas do I use?
The first one.
The first one, yes? You see why the first one? Because if it's x going to 3 minus, it means I'm plugging numbers a little below 3, which means I'm using this formula, right? So what will I get? If you really want to, you can write it initially as 2 times 3 minus, because you're plugging in 3 minus, but that's essentially, you can just write 6, you understand? It's always slightly less than 6, the result, but the limit is what it strives to. It's the border, it's gonna be 6, good? So this is 6, and what about the bottom? The bottom, it's 3 plus, so I use this formula here, so it's 9. So it's 5, 6, 9. Yes? Simple enough, good?
Quick question, you wouldn't do 2 times -3, it wouldn't be -6, it would be 5.
Oh, well, careful, look where the negative is. It's on top of 3, it's not minus 3. It means go to 3, but move to 3 from the left.
Got it.
Yes, so this means just plug in numbers. I tend to be confused by direction easily. So if you, let's say, I tell it to my students, of course, right? So when I drive and I'm excited, I can just turn wherever I like, right? It could be left, right, I don't know. It's usually left is where I think I want to go. So, and when people go tell me turn left, I think left is where my heart is, because I can't remember what's left or right. And then, of course, that's very difficult because I have no heart. Good. So this means just plug in a number smaller than 3. Good. And this means plug a number slightly larger than 3. Easy enough. Yes. So that's why we get 5. Then yes, but be careful from the negative. Yes, you're moving from the negative x-axis, but easiest I think to say plug in numbers slightly smaller than 3, plug in numbers slightly larger than 3. To from left, right, it's up to you if you're good at it, right? This just means slightly more than 3, slightly less than 3. But Alexander's suggestion is right. Good. And this I did it using a table. Again, you understand tables are somewhat misleading because you see there are a lot of numbers not representative here, right? The 3 hat is actually many numbers. It's uncountably many numbers if you actually study infinity. They're just, you plug in, like in that water gun, you plug in countless particles, not just the ones I drew. You understand? You just specify how close they are to the target, to 3. Good? So naturally, we do the following, guys, right? So the limit will exist as long as the left limit and the right limit exist and they are equal to each other. You understand? So if I say approximate by plugging in numbers close to C, take the limit as x goes to C, this limit will only exist if the left-hand limit and the right-hand limit each exists and if they are equal to each other. You agree? Because this is unqualified approximations. I plug in any imitation of C, either smaller than C or larger than C. Good? So let's try to, in this example, notice limit as x goes to 3 does not exist. You can write this empty set sign. You see why? Because if you plug x going to 3 minus, you get 6, but if you go to 3 plus, you get 9. They are not the same values. So the left and right hand limits do exist, but they do not match.
So just to be clear, if it says x to 3, you could either choose the positive or the negative.
Well, you have to do both. You know, for this limit to exist, it means that it's not sensitive to whether you plug in numbers slightly smaller than 3 or slightly larger than 3. So they both must give the same value. And if they do not give the same value, then the limit will not exist.
Oh,
right?
okay,
Then you can say maybe the left-hand limit. So in this example, we just considered the left and right-hand limits. That's called the left-hand limit, and this is called the right-hand limit because you approach 3 from the right, right? Mm-hmm. So right-hand limit, if the number line is the x-axis, you approach from right or you approach from left. Okay. Yeah. So each of those limits do exist, but since they don't match, The
Okay, that
limit
makes sense.
without the plus or minus does not exist. The overall limit does not exist. Thank you, Abraham.
Thank
So
you.
now we talk about limits from graphs. All right, and that doesn't mean limits from a count, right? Or somebody in aristocracy, that just means limit from a picture. You don't know what's a graph, right? What language? A graph is the Russian or German word for count. All right, so here we go, guys. So it's a bit silly, but somewhat exciting. So you go back to playing with dolls, right? And yes, and here is a landscape. So y equals f of x is this landscape, yes? So for any function can generate a landscape which you call a graph. Now, because it's calc 1, this landscape is, how many dimensions are for this landscape? Tell me. This landscape is what dimensional? That's a sidetrack, but I cannot ever avoid it. So Elazar says 2, Sophia says 2-dimensional. Do everybody agrees it's 2-dimensional? Yes? Well, you are wrong. It's not. It's 1-dimensional. Let me explain to you what is dimension quickly. Okay. At least a rough idea of it. Actually, to measure what's dimension is a bit complicated. Okay, so dimension is this is a 1-dimensional space, right? It's a number line. You agree? So let's say here is 0, here is 1, and you are living in this 1-dimensional space. Maybe you drank too much, you know. So you are trying to find the direction to your home, which is located in position 7, right? So your GPS needs to specify, just go to 7, right? To go to position 7, and you know where to go. You just need one number to specify the location of any point of destination. Okay, so that makes it 1-dimensional. Good. Now you understand. So what you're imagining is a ruler with numbers on top of it. Yes. Now tell me, have you seen flexible rulers? Right. Yeah, I can show you one. Right. So would it be any different if I twist it? If I were to twist it, well, and you are attached to walk along this path, will it be any different? How many coordinates do you need to be specified, right? Just the same thing. If the house is at 7 and you were here at 0, you could see, that's how the world looks to you since you have been drinking, right? So it is the same dimension. It's 1-dimensional space. Now, why are you making the mistake and calling it 2-dimensional? Because you are observing that this space is contorting on the board. The board is 2-dimensional. You understand? Now, what's the difference between a 2-dimensional space is you have 2 degrees of freedom. You see, you have to specify 2 coordinates. You see, to get to this point, I need to tell you how much to travel along the x-axis. So let's say maybe this is 7 and maybe this is 8, right? I need to tell you, or maybe 6, more likely 6, I think. Okay, so you need to specify 2 coordinates. You have standing over 7. Your altitude is not specified. You have a freedom to move up or down. At 7, you have a lot of places to go to. So you need to specify 2 coordinates, 6, 7. Yeah. So you need to specify 2 coordinates. That's 2-dimensional space. Yes. Now you, my friends, in which space do you live? 2-dimensional, 1-dimensional, 3-dimensional? What do you think? Most of the time, in what space do you live?
3.
Okay, Sophia says 3. Do you all agree? Well, no, you're not so free, guys. You live in a 2-dimensional space. Why? Because look at it. You walk along you can specify latitude and longitude, and your altitude is already specified for you. Okay, but birds, when they fly, they live in a 3-dimensional space. Or when you go swimming and you dive, you live in a 3-dimensional space. That's you need to be able to specify. You see, in the 3-dimensional space, guys, look at it. You need to specify. You need to be to specify the X, the Y, and the Z axis, you see? But usually when you're walking along a hill, right? So let's say when you're walking somewhere, once you specify your position over the X, Y coordinate, you are forced, your altitude is already determined for you, okay? You understand? You are not a ghost and you cannot fly. And you cannot, and if you tell me what's your latitude and your longitude, I know how high you stand. So you're living in a two-dimensional space, which looks to you three-dimensional because you, well, how do you say that? Because it contorts, because it's a twisted space. And when people speak about twisting spaces, right? When they speak space is twisted, they mean something like that. So three-dimensional space can also be twisted, okay? So this is a twisted two-dimensional space. It's like a twisted sheet of paper. Good. Of course, there is all sorts of other clever and interesting arguments. You see, I can show you a pretty interesting, compelling reason to show you that, because you see, truly, the dimension is the minimum number of coordinates that you have to specify to locate your position. You see, so in this scheme, you need to specify 3, right? But maybe you can somehow specify fewer coordinates and still locate yourself in that space. So if you study analysis, I can show you examples of space filling curves, and they would show you that that all spaces, they can appear in some sense to be one-dimensional, okay? There will be some problem about it. The coordinate will not be unique. So the same position will have many coordinates. That's the thing. But aside from that, you can describe every position in space, even in very high dimensional space, using only one coordinate. It just will not be unique. Yeah, so you're at a fixed height, and my movement is always at that height. Whatever direction I move, my vision is kind of 2D unless I'm flat. So Grant, I mean, with eyes, it's a bit complicated. What I'm saying is, where are you standing? You cannot decide, let's say, you cannot go at sea level and decide to be at elevation of 700 meters, right? If you go to Brighton, I'm presuming it's sea level, right? So it's elevation, when you're going into the water, your elevation is 0, right? You go by Brighton, your elevation will be 0, right? If you were a bird, by the way, advise you to go feed seagulls, right? I have a very, very good way of feeding seagulls, much more interesting than what you can imagine, right? So the seagull is actually able to move in 3 dimensions because the seagull can be over the sea and actually choose whatever elevation it likes. So the seagull is a much, those that can fly are more free than you are, okay? That's why people dream of flying, because they want to be 3-dimensional. Good. Let's move on with the, okay, exactly. If you believe the commercial, just drink Red Bull and get diabetes. All right, so this is a 1-dimensional landscape. I hope I convinced you. Just twist it into dimensional space. You're convinced, yes, guys? It looks like a twisted ruler. So let's calculate some limits. Can you help me? What is f of 5 in this case, guys? Can you help me calculate f of 5, or say it's impossible? What happens to this doll at 5? Well, you see there is a hole. I mean, it's obviously a picture. So that hole means it disappears. It goes, as they say in Russian, к чертовой матери, to the mother of the devil. Okay? It disappears forever, which, by the way, there is a good book by Bulgakov I advise you to read regarding those things. So this is just this is a hole, means the function is undefined. The doll cannot exist at this place. You understand? The doll is confined to that space, but here nothing is there. Nothing exists. Master and Margarita, of course, Alexander. Of course, I am reading it even, you see, for 5th time, and it's so good that I think I should go to sleep at 1, but I end up going to sleep at 5, and always have nightmares, naturally. So it's a very, very good book. You should get a translation. Hopefully English translation will be at least something. The master is Bulgakov. You see, translations are never as good. when it's into another language. Russian translations are amazing. Yes. So guys, f of 5 is undefined. You cannot evaluate it. By this picture, it's undefined. Yes. Now let's look at the limit. What's the limit as x goes to 5 minus? What will be the limit? Could you help me? You see, 5 minus means you put the doll slightly to the left of 5. So the doll is walking here, and where will it be getting? It will be getting to 2. It gets closer and closer to that dangerous place. So this is equal to 2. And what about this? 5 plus, it never changes. Let's say, look at it here. This is 2 plus, and this never changes. So this is always 2.
5 plus. Awesome.
Yes. Y2, Sarah, which ones? Here, look at it. Look at it. You see my pen on the graph? Do you see I'm walking it? I'm walking the x coordinate of that pen towards 5 from the left. Where am I going? It's a picture. It's not serious here, right? It's just trying to illustrate how that appears when you observe limits, right? So you're going towards elevation of 2. The function approaches 2. You see, f of x is the elevation at your position. Your elevation is becoming 2. Good. And here the elevation is actually constantly 2. And then what is the bottom? X going to 5. Does it exist or not? What's the limit?
It exists because the two limits are equal.
Yes, it exists because 2 limits are equal, and the answer is 2. Yeah? Oh, everybody sees it. Yes, guys? Okay. Now help me with this example, guys. It's a little bit weirder, and part of it you might not understand. I will give you other pictures, okay? You see this? Now, what is f of minus 1? Can you see it here? F of minus 1 is where you look at the black curve. What is f of minus 1? Could have been undefined. Of course, look carefully, guys. Here is a black dot, right? It means that there is something there. So it looks like f of minus 1, if you're just evaluating at minus 1, it will be minus 2. Yes. You see this? See this, guys? Minus 2. Yeah? Okay. Everybody sees the minus 2. It's because of this region here. Wonderful. Now, tell me, what is the limit as x goes to minus 1 plus? The B has 2 parts. You see, what is the Grant? B has 2 parts. What is the minus 1 plus? Okay. It looks like, again, it's not a very good picture, but it looks like it will be roughly 1.5. Do you see that? I didn't try to draw it too well, but it appears to be 1.5. You see what you do? You walk the doll towards minus 1 from the right. Beautiful. So it's 1.5, yes? I don't have to write it. It's 1.5, yes? And what happens if I go to minus 1 from the left? It's a bit weird here. Maybe you cannot see with this picture. I'll show you. You cannot draw what I'm trying to draw in some sense, okay? But I will show you what it is. What is B? It's oscillating. You see, so look at it. You begin walking the doll towards minus 1 from the left, and look what happens to the altitude of the doll. Do you see that? It just goes up and down, faster and faster. I mean, in other words, there are more and more hills and valleys, and it just continues going up and down. It's called divergence by oscillation. Okay, it just continues. The curve is just is infinitely folded, so it diverges by oscillation. Maybe you don't believe that such things exist. You cannot draw them, you see, but you can actually physically see them if you do the following. Let me show you here. You see this picture, guys? this is sine of 1 over x. The way, if you ever observe how sine looks like, if you reflect a curve in a spherical mirror, you will see this pattern, because infinity and zero, infinity will be reflected to zero. So you have infinity many oscillations. We are going to study such things later on. You see how dense it is? You cannot really draw it. If you zoom in, you will see more waviness. Okay, so it's called divergent by oscillation. Mathematically, you can observe how that behaves, and physically, you can observe that if you look at mirrors. You can create such a thing in terms of a mirror. Good. What's oscillation is when you move up and down, when you are just you know, like a spring moving up and down. So the doll would be moving up and down, up and down. Yes, well, like banging a tuning fork, exactly. So this goes like this. That's why I call it oscillation. Precisely, Grant. So let's move on. Are you still holding, guys? Alive? We're almost over. We're almost over to begin a question in what, when, where. One question per day. And naturally, we can do office hours if you have some questions. So this limit does not exist. You see, the limit as I go to -1 with a minus will not exist. And because one of the limits does not exist, it's already obvious that this limit will not exist. You see, if x going to -1 makes no sense, because it does not even make sense to move from the left. It's a type of pretty bad non-existence of limit. Okay. Now here we have something we call infinite limits. Okay. So what happens if x goes to 0 of 1 over x squared? So let's look at it, right? So look at it, guys. So I am going to plug numbers close to 0. Plug in plus or minus 1 over 10. And what do you get? You get 1 divided by 1 over 10 squared, and that will be 100. Everybody sees that 1 divided by 1 over 10 squared is 100, right? Do I need to explain it, guys, or you see it? You're not, don't play poker with me, okay? So 1 over 100, if I square it and I take 1 over that, I will get 10,000. If I do it for 1,000, I will get 1,000,000. So you see what's going to happen as x goes towards 0 from either left or right. This quantity will go to something we call infinity, okay? But I want to explain to you that this symbol does not represent infinity, but rather growth without bound. You see, so in our class, what this means, it means that the numbers that I plug in are just growing, and there is no end to how much they can grow. It's like, imagine you take a balloon and fill it with water. Eventually, the balloon is going to be bigger than planet Earth, okay? But it's still finite in size. And then later, it might be bigger than the entire solar system. Still finite in size. Later, maybe bigger than a galaxy, but still finite in size. So this symbol means simply growth without bound. But since saying growth without bound is difficult, you say infinity. Okay, so this limit is infinite. Okay. So we say that if x goes to c of x is infinity, we call this is not this limit does not exist. It's called divergent limit. Why? Because a limit is a particular number. All you're seeing here is that the numbers are just bigger and bigger and bigger. So there is no approaching anything specific. You understand? So in the context of calculus, this is not a point you approach. It's just the numbers are bigger and bigger and bigger. Good? So it's a non-existent limit. Okay? And another thing, it's not a real infinity. So let's try to see what happens with this limit here, guys. Limit as x goes to 3 plus of 2x over x minus 3. Can you solve this particular limit? Let me actually show you. Let's do it together for the 3 plus here, okay? And you will do the second one. Look at it. I can plug a 3 plus in here. If I plug a 3 plus in here, I get 6 on the numerator. And what happens to the bottom? The bottom is 3 plus minus 3, which is slightly more than 0. So it's 0 plus, okay? If I take 6 and divide by 0 plus, That is like taking 6 and dividing by 1 over 10, or 6 dividing by 1 over 100, or 6 dividing by 1 over 1,000. It's like I'm dividing 6 by a tiny number, will give me huge number. So that would be plus infinity. Do you see that? So the idea is this: 6 divided by 1 over 10. That's one approximation of 0 plus will be 60. 6 divided by 1 over 100 will be 600. You understand? So the closer I get to 0, the smaller the number is, the more I'm getting. So this limit is infinity. Good? So this limit is infinity. Would you tell me, please, is the limit, does the limit exist? Based on what I just said, does the limit exist? So we get infinity, does the limit exist in the context of calculus?
You said it's non-existent if it goes to infinity.
Yes, but I mean, doesn't matter what I said. You see why I'm saying what the symbol is doing? The symbol is saying that the numbers are just growing. They're just getting bigger and bigger numbers. And when you think of limits, you're getting something more like a definite number. Do you see? So we would say in this class that it doesn't exist. But I want to warn you, don't worry about this class, is that depending on the context. You understand? So if you study complex analysis, this will be a particular number. Because there is a way, I think maybe even in this class somebody asked me about stereographic projections. There is a way to make it a real number. Okay? Not a real number, sorry. There is a way to make a definite point out of it. But for us, it just means that the numbers are just growing and doesn't look like it's getting anywhere. Now, could you tell me for the left part, limit as x goes to 3 minus, what is this? Exactly. Jasprit, it's exactly what you're saying. So you see what you do here, guys? You plug in a number close to 3, but it's slightly less than 3. So the numerator looks like 6. And the denominator looks like 3 minus minus 3, which will be a 0 minus. So that means a negative number, slightly smaller than 0. That's what it means, right? So if you divide by a negative number, what do you get? You get minus infinity. Good? So you're with me, guys. You understood? I explained it not too fast. Good? I hope not too fast.
Yeah, I'm not following too well, but I guess we can go over this in office hours since we are kind of limited on time.
Yes, less limited on time. We'll try to go over that in office hours. So that ends our lecture. Okay. Let me just show you one question from what, when, where, and then we can do office hours.